My name is Özgür Kartekin. I am from Royal Observatory of Belgium. I am a planetary scientist. I am also the current president of the Planetary and Solar Division of European Geophysical Union. Thank you, Carlo, and the committee to invite me. And welcome all the teachers. I'm sorry I had a slight problem with the travel arrangements. So this was supposed to be an introductory talk to the workshop. Now it's in the middle. So thanks to the other speakers.
It's better than nothing.
Yeah, but I mean, thanks to the other speakers, probably you know now some of the stuff that I'm going to show. So they introduce some of the topics that I will present today so that I can pass quickly. By the way, since I've been traveling for more than 24 hours, I didn't have time to finish the presentation, so it's ongoing. It's a very long presentation, but Carlo will stop me. This is something from almost anywhere in the solar system. You will see a sky, plenty of stars, night sky. It's exciting, it's beautiful. And it's been there for the 4.5 billion years. And anybody, on the surface with some intelligence will wonder where they are coming from, why they are standing there, what do they mean, and how do they move. So this was the, first questions that humanity asked itself. And to understand their nature, we needed to follow them, to understand them. So most of the temples, early temples, were also the observatories, where they meticulously and very carefully observed the motions of the sky. Recently, we just learned that, for example, the ancient Babylonians used geometry to track the planets. And they used some elementary calculus. They used trapezoidal rule, which just gives the velocity versus the time, and you can use the area to calculate the distance. And ancient Greece, we had analog computers, the first analog computers. And also it was possible using the solar rays to estimate the radius of the Earth by looking simply at the shadows at two different locations. This was done by Aristophanes. And also the solar and lunar eclipses, they provided information about our planet itself. So by looking at the stars, we learned something about our planet. And those ideas, they look very preliminary. They were like genius ideas. We're still using them today. And this is called VLBI system. Now, instead of looking at the sun, we are looking at the distant quasars. And we use radio telescopes, more than one radio telescopes. And we look the signals coming at two different locations with slight time difference. And we can calculate the cross-correlate, and we can estimate the changes in the rotation of the Earth, which itself gives information about different physical processes and dynamics of the atmosphere, interior, and we learn many things about our Earth again by looking at the night sky or at the distant objects in the solar system or beyond. Also, the astronomy has been the father of the natural sciences, I can say, that allow us to establish any scientific reasons, which is very basic, actually. We observe, like we observe the sky objects, then we think, we try to understand, and then we develop some theories, and we verify that by measurements. That's what has been done. And in order to understand, to really understand what's going on, we need the observations. Without that, we cannot really prove or understand what's going on. And this is a very early solar system schematic. So Earth was always at the center, which is normal. As the first image I saw, the sky and the stars, they are rotating around us. So it was, logical to put the Earth there and the other planets and the sun beyond. The interesting point when we start to look at the positions in the sky of the planets, then, for example, Mars had a retrograde motion. How you explain that? The theory has to be changed, but they added, small spheres, epicycles there. Then, okay, then it fit better. But then that was good enough for the precision of the observation we had at that time. And that led that theory has been used through the Middle Ages. This is a picture from Dante's Divine Comedy, for example. But once we had more information, more data, for example, Copernicus, he came with an idea which fit much better to the observations where the sun was in the middle. But again, he was saying at that time that he wasn't able to predict Mars' position correctly, even with that theory. Then we had to wait precise measurements by Brahe and Copernicus, and then we established the laws of the orbital motion. That was the Kepler's theories for the law of planetary motions. And you can see that the planets are rotating around sun in elliptic orbits. And where they're close to the sun, for example, they move faster, and they go slower there when they go faster. And those laws, actually applying them, Kepler, he showed that the positions of the Mars, for example, as a function of time in 17th century, this is showing the Kepler theory, and this is the uncertainties, error in the positions, actually, estimated positions, and that shows that this theory was good compared to the previous one. That's thanks to the observation that we had to come with that, with that theory. And we need to get more data to better understand. So that's what we are doing in planetary sciences. In astronomy, we are observing the solar systems and beyond. And this is, as you know, our solar system as we understand today. The sun takes much of the mass of our solar systems. We are at the we are just over there. But the microphone closer. Oh, sorry, yeah. But the main question is still like standing. Even we know the orbital dynamics since 17th century well. Where are our origins? How the solar system was formed? And this is an important question, and for that one also we need some observations. And we see in the sky, this is an image from the Hubble of the Eagle Nebula. This is M16 and Messier objects. It's in the Milky Way, about 7,000 light years away. And it's a beautiful image, that one. It's called the Pillars of the Creations. And the distances are amazing. So one pillar makes almost 4 light years. And the dust and the gas that composes that nebula, it's maybe on micron sizes. So there are like different scales that we're talking here, from light years to the micron scales. And these are the places where the stars, they are born and they die, and we think that they are also linked to the creation of the stars and their solar systems. So you see from a dust and gas cloud the formation in the middle with a creation with mass and high pressure, a sun, a star. And when it reaches enough temperature and pressure and the conditions are established, it creates to start its fusions. And then also you see the formation of the first planets around. And as they move around, around the central objects, they accumulate the mass, they accreate. So that's how the planets are created. And and this is what we think the solar system was established. And as I said, the examples are in the universe, and Hubble helps us to understand this formation. But there are many details there we don't really understand well. For example, one of the main aspects is how do you go from this little dust and gas grains to the planets? And the time scales are enormous. What are the exact procedures? And then once you create the planetesimals, then by collisional accretions, we create the solar system bodies, the planets. But then the same kind of collision, the inverse, they can also destroy them. They disrupt them. So in the late phases, we can destroy those planets. So we're creating and we're destroying. And we believe that most of this phenomena passed or occurred very early in the formation of the solar system. Then we created the solar system, the planets, and by looking at them, actually we see that the small ones, the terrestrial ones, Mercury, Venus, Earth, Mars, they're close to the sun. We have the gas giants there, and we have like small dwarf planets we call Pluto and Eris. And there's been a long debate, what is a planet? And International Astronomical Union came with the following definitions, which say simply that the planet is a celestial body orbiting sun. So everybody agrees on that one. It has to have sufficient mass so that its gravity to overcome rigid body forces. So basically it says that it should be round, the shape. And the third one, it has to clear the neighborhood. So when we saw in the previous video, when we were creating the planets, I mean, they're like, some of them, they're accumulating, they're getting the mass. Some of them, they pass those phases and they clear their orbits, they're planets. The other ones that they didn't clear the paths, they're still crossing the other ones and their possible impacts and collisions, they're called dwarf planets. And all the rest, we call them small solar system bodies. So, after the creation of the solar system, and we observe and we have the impression that that's a stable and orderly system. We have the asteroid belt. We have a frost line that Athena just mentioned. So we have the terrestrial planets close to the sun, and then we have the gas giants and water objects, water-rich objects beyond there, and then we have the CH4 freeze line, and you know, the image looks okay, and we thought that maybe for the last 4.5 years, 4.5 billion years, it was the case. But when you look again closely and look at the details of the formation, it turned out that Uranus and Neptune, which are far away, they should be much smaller, because on the nebula there was much less material there. They are much bigger than they are supposed to be. Also, the formation of Mars was problematic, and the presence of asteroid belt wasn't easily modeled or explained by any models. So these were the problems with those theories. And a group of researchers in 2005 from France mainly, but the internal collaboration, they proposed a nice model actually. And so actually, this is the origin of the solar systems when we have the gas giants. So these 4 orbits, they correspond to the orbits of Jupiter, Saturn, Uranus, and Neptune. They start, but then after a while, they start to get into resonance, Jupiter and Saturn, and then they change, the positions they change. This is very complex orbital dynamics, but the idea is simple, is that you start from a place, when they start to enter to the resonance, Jupiter and Saturn, then the orbits, they're all influenced. So what happens is that Neptune goes back, Uranus goes beyond, you know, far away, and also this explains somehow the asteroids, but and this was a very good and actually revolutionary way of thinking, because it simply says that after the formation, the solar system continued to evolve, and we had the migration of the gas giants. This is another video showing actually that processes. This is our numerical simulations. And so in that one, you see from the top view of the solar systems with the orbits of the Jupiter, Saturn, etc. You will see that they will enter and they will clear this area. And this is the terrestrial planets. And you can form and you can destroy planets by small impacts there. So we'll see this, the time scale is on the top of this video. Of course, they are not exactly the time scale, so it's not corresponding to time exactly from one video to another one. It should be happening by now. You see, it starts to oscillate a little bit, the orbits. They get unstable, and then whoop. And they find, again, their equilibrium positions. That's very interesting, because that happened probably 5 million years later than the formation of the solar system. And what we see today on the moon or Mars, the big impacts, the studies show that most of this impact they happened about 4 billion years ago. And there is a big discussion among the scientists what was the cause of that? Was it correct? Some of the scientists say that the data is not really accurate. Some others says, no, there should be a peak in the collisions in the solar systems. And this model actually they provided that, okay, 500 million years, 5 billion years, so, sorry, 0.5 billion years later, you can have such a procedure that will, send all the asteroids and small objects to the inner solar system, and you can bombard Earth included, Moon, Mars, all the inner solar system objects. So this is something become unimaginable maybe 10, 15 years ago, but now it's well-established theory. So Jupiter and Saturn, they migrate inward, and almost at the position of the Mars today. And then they move back. And that's how, we have Mercury, Mars, Venus, Mars here. And this theory was able to explain well also the asteroid belts, which is actually a mixture of, rocky objects that you see by red, and the more, the rocky objects there, and then the blue ones with the water-rich objects. Because today in the asteroid belt, we see the combination of two types mainly. It's water and the rock types. And that's one of the explanation, or the best explanation that we have today is due to the gas giants, their migration. And that's again the same idea. We have the disk of rock planetesimals and disk of water-rich carbon-rich planetesimals. And due to this migration procedure theory, we end up with a mixture of them in the asteroid belt. And this shows, as a function of eccentricity and semi-major axis from the distance from the sun, the migration process of the big giants, and then the creation of the asteroid belt there. So the solar system is created now, and about this very dynamic and very let's say the impacts, very energetic processes. Where do we see their signatures? And the place where we see is mostly on the moon. When we look on the surface of the moon, we see many craters. And that shows the sign that, okay, that happened, tragic things there, a lot of impacts. And when did they happen, and how did they happen, and how did they influence the evolution of the moon? And that's another video from NASA, a lunar reconnaissance orbiter, actually. The data was used, the spacecraft. And this is not the only one. This is, one of the places where we know the best, because we have Earth-based observation and we have spacecraft. So basically, Moon formed like all the rest of the solar body objects 4.5 billion years ago. There was a big impact with the Earth. But okay, that will start later on. So it starts to cool down. So we have a solid surface. And then we start to have the impacts. The South Pole Aitken Basin that we see on the moon today, it was created by a giant impact, and the impact affected almost the other side of the moon also. So this was a big impact. And then we come to the late heavy bombardment phase, where due to the migration of the gas giants, we start to have increased number of impacts. This happened between 3.8 and 4.1 billion years ago. So moon surface was bombarded, it's called bombardment, by the impacts. That caused, of course, the increase of the temperatures. And also the interior of the moon wasn't cool enough, so it was still a little magma. And it created actually this magma oceans in the surface that started to cause, it's called microvolcanism. So due to the impacts, they affected the interior. There was much more increased magma activity. Then it started to cool down, and we see the difference. Today you can see to the moon, and you can see some dark and clear spaces. So this is like Iron Ridge, this is magma, mare, lunar mare. It was created like that. Of course, the cratering and the impacts continue, but with much less and less start to occur. So in time, it decreased. We didn't have that big impacts that happened during the late heavy bombardment. Even today, we have the impacts on moon, like on the Earth, but those really hardly make any changes. Some of the craters, about 1 million years, we can see that, but most of the moon phase, moon shape that we see, it dates from 3.8 billion years ago. So that's what we have today. And most of the other planets, they were formed about the same, process. So they all suffered the impacts in the past. And some of them, their surfaces, as you probably saw in the lectures, very old, like the moon, the Mercury. You can see a lot of impacts. And some of them, they're changing on the Earth's surface by all dynamical processes that we have. And in the atmosphere, for example, the rivers, the seas, they change the surface. Well, we don't see on the Earth as old as the surface on Mars or the planets. This is very important. By looking at those planets that have old surfaces, these are like kind of, frozen, let's say, proofs of what happened. So we can go there and understand, because on the Earth we don't have those signatures. So what happened in the solar system, we'll learn by looking to the moon, Mercury, Mars, the places where the surface is old. And as you heard probably, their rotations all different, their orbital dynamics all different. They all had, different evolutions, slightly. And what is interesting, actually, this was a concept. Okay, let me talk that one. So this was the idea, even end of 19th century, we know the planets. We didn't go there. So we had just the imagination from the Earth-based observation, what they look. Moon, it was the best we know. But Mars and Venus, we had to go there to understand what's their surface, if they're habitable or not. For that, we need to do planetary missions, space age. So this shows, a summary. It's a very complex diagram of the planetary missions that are currently occurring in the solar systems. So the sun is over there with the Earth. So there's a zoom for the Earth and Mars. As you can see, those are the two bodies which are intensively studied. We have also the Jupiter system there. And there's a good reason to study Earth and Mars that intensively. I mean, Earth, as you know, it's our own planet. But Mars, we have so many spacecraft around. Phobos and Deimos, those are the two natural moons of Mars. And those are the spacecraft. The Maven is the latest one who arrived. And we have Mars Express. We have Triska's orbiter will come there. So that goes now only with Maven. But we have different spacecraft that are currently observing Moon. Mars. And this image is taken from the Mars Express orbiter. This is not a very high definition video, but it's taken by the navigation camera of the Mars Express as it orbits Mars. So you can see, as I showed, so this passes over the pole. You can see the CO2 poles on the Mars, and it's going back. So as it says Kepler's law, when it comes closer, it goes faster, very fast, and it comes there. It's slowly going now, and it will pass quickly above the surface. It's an elliptic orbit, Mars Express. And it's bringing a lot of information and images from the Mars. And we can do this kind of calculation with Newtonian mechanics, most of them. And we have also rovers on the surface. This is a different generation of rovers. And the latest one is the Mars Science Laboratory on the surface by NASA. You can see the changes in the dimension of the rovers over the last 10 years or 15 years. From small ones, we really went to almost a car size. And this is a video on the surface. We're moving with the Opportunity rover, getting out of the crater. And this provides us the real images on the surface. We know what they look like. I don't know, can you tell me which one is from the Mars? These images, they're taken from the 5 different planets, actually. That one, yeah, that's right. That's right. And this one is coming from an asteroid, Itokawa. This is the moon. This is the Venus surface. We had some Russian probes that landed in the 80s. Mars, Titan, the Huygens probe, and Earth, as you know all. And what is interesting in terms of planetary science or comparative planetology is to look at the Earth and to compare it with its neighbors. Like Athena said Venus is there. It has an atmosphere, but it has a greenhouse effect, which makes it hottest planet in the solar system, actually. Mercury is closest to the sun, but it is Venus, which is really having the surface temperature that are high, very high, wherever in the solar system. Moon and Mercury, they almost no atmosphere. They have very tiny atmosphere. And Earth, it's a wonderful place to live with the atmosphere and etc. Mars, it used to be probably a nice place, might be, but today the atmosphere lost most of the atmosphere. It has a tiny atmosphere left. And we want to understand why. How the planets, they change, how do they evolve, and how do they affect to the habitability. This is the main driving force to study Mars. And this is an image. I mean, it could be also the Earth, but you can see the clouds actually moving in the sky. I don't know if you can see there. And this is a video, I mean, image taken from a Mars orbiter. You can see the thin atmosphere. And this is the Cape Point. How did it lose its atmosphere? And we are still working. And the MAVEN spacecraft that came recently on the orbit of Mars is going to look actually the escape processes. But you know, when you come back to the Earth and look at the Earth's atmosphere, it's not much, you know, thicker, because compared to the size of the planet, the atmosphere is always thin. Of course, it's like, you know, 2 orders of magnitude larger, the Earth's atmosphere. But this image is taken from the ISS. Shows also that we have actually not such a big atmosphere compared to Titan, etc. It's a tiny and fragile atmosphere we have. So it's important to understand what caused the Mars atmosphere escape or change may have implication for us, for our future. How much time do I have?
Another 12 minutes.
Okay, then I can continue. So let's see. Do you have any idea where this image from? Mars. Yes, of course, yeah. This is the sunset. And from the Mars, you can see actually the Earth, and they took the pictures. And this is also from the orbit of the Mars. This has taken an image of the moon and the Earth system. And just to say that, okay, Earth is another planet. In order to understand the planets, we have to study Earth, also the other planets. Otherwise, we will not, you know the past or the future of the Earth. It will be very difficult with only one example that we have. Okay, that's why we want to explore the space. And Athena just showed that one. This is ESA's fleet. They're exploring the solar system. And the most recent one, it's the Trace Gas Orbiter, which was launched on the 14th of March from Kazakhstan. And it was a successful launch, and they're testing actually the instruments, and everything is working perfectly fine. It will arrive on Mars on October this year. It will land a surface probe. It will be the first European surface probe on the surface of Mars. It will make measurements for 5 days. And there will be a trace gas orbiter, which will enter to the orbit. It will take almost a year to slow down and to put in a circular orbit, because as you see, Mars Express had an elliptic orbit. We want to go to a circular orbit for better observations. With the elliptical one, you have to come very close, and only one part of the trajectory you can use to make those measurements. So this is the ExoMars image, and the objectives, main objectives of the trace gas orbiter, to understand the atmosphere. The little components of the atmosphere we call trace gases. Methane is one of the main components we want to understand. It's like the Earth, methane exists, and we don't know its source. Can it be, why is there? It's not easy to understand. It was a big surprise, because into the chemistry of Mars, it should have been destroyed. So there's a source of methane, and more importantly, maybe scientifically, there's a sink of methane, and they are not explained. And this plot just shows different methane sources and sinks. And Sushil Etreya will give a wonderful talk on Friday. He's the planetary science medalist on the methane in the solar system. And there will be a rover in 2018, and with some cameras, and it will look actually the places where to drill and to look at the ancient habitats for habitability. This is, again, a picture taken from the surface of Mars. And this is, again, the rover. And you can see a dust devil behind. It's something that we see on the Earth also, those dust devils. These images, they're taken from the surface of Mars. These are the dust devil that's moving. And this is just a comparison of what we have on the Earth. We have, the physics is not very different. The same physics applies on the surface of the Mars and other planets. Just the conditions are different. And maybe the most intriguing questions on Mars is the presence of water. Is there liquid water? And we see some, signatures on the surface. And the seasons change, the time changes, the strikes, they become darker. Are they water, or can it be CO2? And there's more and more evidence from the spacecraft that shows that this and models, that you have to also apply your models, because we don't see everything, we just see those things. And we apply the models and we verify that with the observations. And there's more and more evidence with spectroscopy and with the images. We think that the water, liquid water, is existing on the surface of Mars as a function of a certain time of the year, during this slopes, actually, at the slopes, at the craters close to the equator. And this is another movie from, we're just going to the surface and looking at the crater rim. So that's where we see the water. At least the signature of the water. And again, you will see here, so what we do is every year you go, like same seasons, the same time, you have to see if this is periodic, is it happening every season, or is it like just once? Because if this is once, it can be something, a landslide, or could be. But we see that different places, different times, but always periodic in seasons, so there's a seasonal variations. And unfortunately, we don't know 100% it's water. A lot of people think it's water because it's also there are salts. So the model, when you make the water with the salts, you can make theoretical models, and you can say that these are water signatures, and most likely they are water. But that can be also CO2. Some scientists, they say with CO2, because on Mars, like we have on the Earth, they have a CO2 cycle. That will be the next big thing to look on the Mars with the rovers. But that's exciting. And as I said, on Mars, we think like on the moon we had a magma ocean, magnetic field, but the evolution is amazing. We don't understand most of the phases. We have the estimation there was, one part, maybe one time in the history, water there on the surface. But they created Wally network. We see this geological evidence. But today it become all dry, so we want to understand the evolution. So the Mars adventure will continue, and the exploration of the solar system will continue. And I think more things we'll learn, more observation we make, as you see, more questions come. That's the natural way the science goes. And I think you should be, stay tuned for the next, phases of the exploration. Thank you very much.
Thank you.